Hello friends, I welcome you in lecture number 4 on higher order partial differential equations. Recently we are discussing how to solve homogeneous linear partial differential equations with constant coefficients, and we are considering that this capital F, which is a function of d and d dash, is homogeneous in d and d dash. If f is not homogeneous in d and d dash, then we will understand in upcoming lectures that how to write down the general solution. But recently we are discussing those linear PDEs with constant coefficients which are homogeneous and in which this capital F is a function of d and d dash. And as we have discussed that, first we are writing the auxiliary equation by replacing capital D by small m, capital D dash by 1 and equating to 0, and then after solving the auxiliary equation, depending upon the roots of auxiliary equation, we are writing the formula for the general solution. Now in this lecture we are going to discuss one special situation in which our function of d and d dash will be having some power of d and d dash in the product. For example, I can have d times d square minus say d dash square. Suppose my function of d and d dash is like this, or it can be in this form, and then we can take this d common, d times d dash square. Suppose our function of d and d dash is in this form. So whenever we have this type of situation, we will have some power of d in the product and we will have some another factor. So whenever we have this type of situation, we have to write down the part of general solution corresponding to this factor d separately. For that we can understand in this way. Suppose our equation is f of d dash z equal to 0, where this f d d dash is there, that is d cube minus, this is the equation, d cube minus d dash square z equal to 0. This means I can rewrite this as, if I take d common, I have d square minus d dash square z equal to 0. And now from this I can write that I can have dz equal to 0 and d square minus d dash square z equal to 0. Now how to solve this dz equal to 0? So we can write down the auxiliary equation corresponding to this d, and for that we replace d by m and we will have m equal to 0, and the part of solution corresponding to value of m is written as arbitrary function of y plus mx, and m is 0, therefore we have arbitrary function of y, that is phi 1 y will be corresponding to this part capital D, and here we will write m square minus 1 equal to 0, that is m equal to 1 and minus 1. Therefore here I will have two functions. For m equal to 1 I will write phi 2 of y plus x, and for m equal to minus 1 I will write phi 3 of y plus mx, m is minus 1, and then we will add these three functions to write down the general solution. But suppose instead of d we have d dash in the product, then you can observe this situation. Suppose I have this type of situation, d dash times d square minus d dash square z equal to 0, then I can rewrite this as d dash z equal to 0 and d square minus d dash square z equal to 0, that is this part. So corresponding to this portion, we will write this as the part of general solution, d square minus d dash square z equal to 0. Now what about this? We write down the auxiliary equation by replacing d by m and d dash by 1. So if I replace d dash by 1 in this function of d and d dash, then I will obtain 1 equal to 0. That is a contradiction. So what should we do in this situation? If I have d dash z equal to 0, then what will be the part of general solution corresponding to d dash z equal to 0? So for that we can use direct integration. We can write d dash z equal to 0 as partial derivative of z with respect to y equal to 0, and if I integrate both sides with respect to y partially, that is I will consider x as constant, then this is equal to integral of 0 with respect to y plus some arbitrary constant. But here we are integrating z with respect to y, and z is function of two variables x and y. We are considering x as constant, therefore arbitrary constant can be a function of x also. So instead of writing plus c as arbitrary constant, I will write arbitrary function of x as arbitrary constant, and from this integral of del z by del y is z, integral of 0 is 0, and I will have arbitrary function of x. So whenever I have d dash in the product in fd d dash, then the part of general solution corresponding to d dash will be written as arbitrary function of x. And whenever we have d in the product, as in this case dz equal to 0, then the part of general solution corresponding to d will be written as arbitrary function of y, and part of general solution corresponding to d dash will be written as arbitrary function of x. Now sometimes we can have repeated factor also. Instead of d, I can have d square or d dash cube also. So what should I write in that case? Suppose I have d square in the product, then I will have d square z equal to 0, and for d square auxiliary equation will be m square equal to 0, that is m equal to 0 repeated 2 times. Therefore corresponding to m equal to 0, I will write phi 1 of y plus 0x, that is phi 1 y. Again 0 is repeated, so phi 2 of y plus 0x, which is phi 2 y, and here I will multiply by x. So whenever I have d square in the product, then the general part of general solution corresponding to d square will be written as phi 1 y plus x times phi 2 y equal to 0. But if I have d dash square z equal to 0, then here I cannot write down auxiliary equation by replacing d dash by 1. So in that case I will apply again the method of integral. This I can rewrite as del square z by del y equal to 0, and now I can rewrite this del square z by del y square as del by del y of del z by del y, and I again integrate both sides with respect to y, and I consider x as constant. Integral of 0 is 0, and because we are considering x as constant, we have to write arbitrary constant as a function of x. Now what is integral of this del z by del y with respect to y? Del z by del y itself, that is equal to arbitrary function of x. And to obtain z, again I have to integrate this both sides with respect to y, and again I consider x as constant. So integral of phi 1 x with respect to y plus arbitrary constant, that is also going to be another function of x denoted by phi 2x. What is integral here? Z. Here phi 1 x is independent of y, so it is considered as constant, integral of dy is y plus phi to x. So you can see whenever I have d dash square in the product, then the part of general solution will be arbitrary function of x plus y power into another arbitrary function of x. This we can generalize for third power of d dash also. The part of general solution corresponding to d dash power 3 will be equal to arbitrary function of x plus y times another arbitrary function of x plus y square times another arbitrary function of x. So you have to remember this, and if you forget, you can use this type of direct integration to write down the part of general solution corresponding to power of d dash. Similarly, if I have third power of d, that is derivative with respect to x, then the part of general solution will be arbitrary function of y plus x times another arbitrary function of y plus x square times arbitrary function of y. If I have d to the power something, that is d raised to 3 here, then I will write 3 arbitrary functions of y and I will keep multiplying up to second power of x. Similarly, if I have d dash to the power 3, then I will consider arbitrary functions of x, 3 arbitrary functions of x, and I will multiply up to y square. So in general, suppose I have d to the power m. D to the power m, d stands for derivative with respect to x. Therefore, arbitrary function will be function of y. So we will write m arbitrary functions of y. Phi 1y, phi 2y, phi 3y, and so on up to phi m y. And because power is m, we will multiply by powers of x up to x raised to m minus 1. And if I have d dash to the power m, then I will write down m arbitrary functions of x, say phi 1x, phi 2x, phi 3x, and so on, phi m x, and I will multiply by powers of y up to m minus 1th power. If I have m here, I will go up to m minus 1th power of x or y. If I have d, that is d stands for partial derivative with respect to x, then I will write arbitrary functions of y. And if I have d dash, then I will write arbitrary functions of x. So whenever you are writing the general solution corresponding to this type of linear homogeneous partial differential equation with constant coefficients, then first observe that whether this fd d dash contains any power of d or d dash, and write down the part of general solution corresponding to that power also. So all these things I have written, and I am considering some examples to explain this. Suppose we consider this differential equation, d cube minus 4d square times d dash plus 4d d dash square z equal to 0. So here we can see we can take d common, and we are left with d square minus 4d d dash plus 4d dash square z equal to 0. And therefore I can rewrite this as dz equal to 0 and d square minus 4d d dash plus 4d dash square z equal to 0. We know that corresponding to d, we have to write arbitrary function of y, because here power of d is 1. We will write only one arbitrary function of y in the general solution, and here I have to write down the auxiliary equation by replacing d by m and d dash by 1. So here I have m square minus 4m plus 4 equated to 0, and this is nothing but square of m minus 2. Therefore here I have m equal to 2 comma 2, and now we write down the general solution. Therefore the general solution is z equal to, first I am writing this corresponding to power of d, that is arbitrary function of y denoted by phi 1. Corresponding to m equal to 2, I have to write another function of y plus mx, m is 2, and plus another arbitrary function of y plus mx and multiplied with x. Here phi 1, phi 2, phi 3 are arbitrary functions of x. What is new thing here? That this left hand side contains in the product power of d, and corresponding to d we are writing arbitrary function of y. Another example, here we have homogeneous function of degree 4, and we can rewrite this. You can see from each term I can take d into d dash common, and here I am left with d square minus 4d d dash plus 4 times d dash square z equal to 0. So here I have d in the product and d dash is also in the product. So this I can rewrite as dz equal to 0, d dash z equal to 0, and d square minus 4d d dash plus 4 d dash square z equal to 0. Corresponding to d, I will write down arbitrary function of y as I have discussed. Corresponding to d dash, I will write down arbitrary function of x, and I have to think for this. So for this equation, as I discussed in previous example, we will get this same auxiliary equation, m square minus 4m plus 4 equal to 0, and this is nothing but square of m minus 2 equal to 0. Therefore we have repeated roots m equal to 2 comma 2, and therefore what is general solution? Z equal to, corresponding to d we write down arbitrary function of y, corresponding to d dash we write down arbitrary function of x, and corresponding to m equal to 2 we write down arbitrary function of y plus 2x, and 2 is repeated, so we multiply another function of y plus 2x by x. And here new thing is we have single power of d and d dash in the product in fd d dash. Another example, d cube times d dash square plus d square times d dash cube z equal to 0. If you observe, we can take d square into d dash square common, and here we are left with d, and here we are left with d dash z equal to 0. And first we solve this. We have d plus d dash z equal to 0, and if I replace d by m and d dash by 1, auxiliary equation corresponding to this equation is m plus 1 equal to 0, that is m equal to minus 1. And here I have d square in the product, d dash square in the product, so I have to write down the parts corresponding to d square and d dash square. So the general solution is z equal to, corresponding to d square I have to write two arbitrary functions of y denoted by phi 1y and phi 2y, and I have to multiply by x. This corresponds to capital D square. This is part of general solution corresponding to d square. And corresponding to d dash square, I have to write down two arbitrary functions of x, phi 3x and plus phi 4x, and I have to multiply by y. This corresponds to d dash square, and plus corresponding to m equal to minus 1, I have to write arbitrary function of y plus mx. M is minus 1, that is arbitrary function of y minus x. So remember, corresponding to d square, this is the part of general solution. This is the part of general solution corresponding to d dash square, and this corresponds to m equal to minus 1. So in this way, we have to remember that whenever we have mth power of d in the product of fd in the product in fd dash, then corresponding to d raised to m, part of general solution is, we have to write down m arbitrary functions of y, say phi 1, phi 2 up to phi m y, and we have to multiply up to m minus 1th power of x, and corresponding to d dash raised to m, we are writing m arbitrary functions of x, and we are multiplying by powers of y. So up to y raised to m minus 1 phi m x. If I have d dash, then arbitrary functions are of variable x, because d dash stands for partial derivative with respect to y. So while integrating with respect to y, we will consider x as constant, therefore we are writing arbitrary function of x. And whenever I have d, d stands for partial derivative with respect to x. So while integrating with respect to x, we will consider y as constant, therefore here we are writing arbitrary functions of y. So remember this criteria also while solving homogeneous linear PDEs with constant coefficients, in which this fd d dash is a homogeneous function of d and d dash. And this is all about this session. In upcoming session, we will discuss the method of solving non-homogeneous linear partial differential equations with constant coefficients, in which right hand side will be non-zero function of x and y. So I stop here. Thanks for watching.